Have any of you guys went home and did that derivation of belief propagation over the cycle in different directions? So remember that square 4-node graphical model we did last time, and we mentioned that doing just brute force belief propagation isn't a good idea because depending on which direction you send messages, you're going to get two different type of answers. So I hope you guys go home and do this kind of little derivation, which really is very little, so that you can get a sense about how message passing or how information propagation on a graph behaves, and why a graphic model is a good tool to guide your computation. So we have a few slides left from last lecture. I'm going to go through them very quickly, but the main focus on today is to prepare for our next important topic for graphic model, which is about parameter learning. We're going to introduce a canonical representation of graphic model parameterizations, so that you can do the learning problem systematically. Again, I already got feedbacks from many students that the pace of the class is rather fast. If you compare the speed of what I cover here to, say, what you see in Coursera or maybe other places, say Daphne Collard's course in Stanford, we are about twice as fast as they are. Okay, and there's a good reason for that because in fact, if you prefer a slower speed, since that class is already available, you are encouraged to go there and watch that movie. That's actually very good. The reason I want to do faster is because I want to make this class not necessarily advanced, but I want to make this class really useful for you to apply to a real problem, so that at the end of the semester, you don't just go with a bunch of definitions and the formalisms. You actually can apply some of the model at least directly to your problem at hand, and then be able to write papers. So I think in about 2 or 3 lectures, we are going to get to the kind of the contemporary practice of graphic models, and over there you actually will see a lot of techniques being directly useful for your current problems at hand. But here we are still in the basic foundation, which is about already midterm speed in the alternative versions of this class. But hopefully you can bear with that. And I also give a lot of reading assignments, and that will also help you to prepare many of the materials that I'm going to skip actually during the class. All right, so just to review a little bit, we said that the truly nice behaving representation of a graphic model that is going to support consistent and correct exact inference. Remember, I use a lot of qualifiers: consistent, effective, and exact. Exact inference is this junction tree algorithm, and there are a lot of equivalent definitions of junction tree, and you should remember what those definitions are. One of the key properties of a junction tree is this what? Someone want to remind me about that? If 2 variables are in 2 separate, if the same variable or same set of variables are in 2 different cliques, then what kind of tree of cliques is called a junction tree? That's the essence of why we need a junction tree. Okay, let me remind you, this is about the running intersection property. Any subset of nodes, if they are in multiple cliques, then they should also appear along the path that connects multiple cliques, so that they can always invoke a local consistent type of constraint on the message, so that they can actually be not only locally consistent and globally consistent. If you still don't have a good feeling about this property, you should go home and read the textbook materials from both Mike's book and from Daphne's book. Okay? And here I'm going to just assume you know all this. And then here is actually a procedure that constructs the junction tree. You first need to moralize the graph. Remember what is moralization. And then you need to triangulate the graph to close any loops which contain more than 4 nodes. And then you're going to build a clique tree, okay, which could be a maximum spanning tree, on the cliques. And again, there are a number of detailed illustrations of these algorithms on the book. And these 3 steps ensures a junction tree with the random intersection property. And then you are going to run belief propagations, which is now a local message passing protocol, because in this case, on the junction tree, local consistency guarantees global consistency. Okay? And here is roughly an illustration of such a tree. Once it is a tree, you can always hand the tree in a unidirectional way so that you can have a collection step and a distribution step to make sure that on every edge in this tree of cliques, the messages are passed back and forth twice, okay, altogether. And these are the protocols for the message passing. One algorithm is called the Hugin updates, which is about updating 2 types of potentials. One is the potential function defined on the separator clique. The other is the potential function defined on the marginal, the standard clique. And they kind of use a recalibration of the potential functions. Another type of updates is maybe more familiar to the original propagation algorithm on a standard tree, which is known as the Schaefer-Shanoy updates. Here you can see that generically every message, no matter where it comes from and where it goes to, it's actually defined by a sum product operation. It is product over all the messages into the clique, okay, plus all the potential functions that includes elements in the clique. Then you're going to sum over, all the variables that is outside of the intersection between 2 cliques, and they're going to send the remainder to the other clique, which is intersecting with this one, but supposed to receive the message. Okay, just remember this by heart. And here are a number of illustrations. Right, this is a junction tree or a clique tree we built before, and you can see a definition of one of these messages coming from here to here. You can see literally how the definition was practiced in here. 2 messages from here and here, plus a potential function defined on this clique only. Okay, and you should also be able to now understand these very famous forward algorithms in HMM now clearly. Right, how I have this HMM, which is already a junction tree. If you recognize, right here, you have a clique, you have a clique, you have a clique, and by defining, potential functions on these different cliques and draw a correspondence graph, you actually will see a clique tree. And then here is a message basically sent from one clique to the other clique. Okay, you can kind of see this already. This is a same message from the previous one, and this is what? This is the transition probability, which can be understood as the potential functions on the clique, right? And what is this? This is the emission probability, which is the potential function on this kind of clique. And that 3 multiplied together to form a message. And the sum operation now is moved inside because the argument in the summation operator isn't touching anything in this particular equation. Okay, and once you did all this message passing often enough, you are going to actually get the last message, and that gives you a way of generating the marginal likelihood of only the observation sequence. Okay, so go through this again, very carefully, and then you can get some good insight about the junction tree algorithm. And here again, I just want to reiterate this Schaefer-Shanoy, the forward algorithm as an example of the Schaefer-Shanoy. You can see the nice correspondence of what we see here and what we're seeing here. Okay. And likewise, for the backward message passing, backward algorithms, you have the same thing. The message is not coming from here to here, and you have the downstream message I think this is the conditional probability, which is a potential function on this clique, and this is a emission probability capturing the observations. Okay, so all I'm trying to say is that most, if not, I think all of the exact inference algorithm now you actually will be running into in textbook or in real life, are likely to be an example or instance of the very general junction tree algorithm. So that's basically the value of understanding junction tree. It is a way to unify a lot of different algorithms, and you need to remember only now one algorithm rather than every specific algorithms. So with that, I close. Here are the take-home messages. Okay, you want to now understand what is a junction tree, what it is used for. It is used for exact inference, and by definition, junction tree algorithm can be intractable if you have a very strange graph, like the Ising model or some other model whose tree width is very big, no matter how you create the junction tree, or no matter how you do the elimination ordering to actually produce the smallest possible intermediate cliques. Right? There are some cases you just cannot go smaller. And then the message passing algorithms have two different styles, Schaefer-Shanoy, and the other is called the Hugin updates. And algorithms for building junction tree is also described in the book. Any questions before I now move out of exact inference? Okay, I intentionally spent not too much time on exact inference because life is brutal. There aren't too many graphic models which can be dealt with by exact inference algorithms. So I don't feel it's beneficial to spend 5 lectures covering all instances of exact inference. Most of the models are going to run into will be approximate inference algorithm. That's where we're going to spend more time on. Okay? All right. So now let's start our discussion of canonical parameterizations of graphic model so that we can, again, develop a generic approach to learning. Okay, learning in here means parameter estimation. I'm going to define learning more exactly in next lecture, but today is going to be preparing us for that. So as I mentioned, the quantitative aspect of graphic model is that once you are given this graph, you are going to put there some local conditional distributions or potential functions, and so that the graph can be coupled with some numbers or some numerical characteristics. And here I give you 2 examples. So in this case, you have all discrete random variables. And very obviously, you can use a table to represent a local conditional distribution, right? And here I have 3 parameters, 3 random variables that are all continuous. Say this is we can assume this is a Gaussian variable, this is a Gaussian variable, and this is another Gaussian. Then one way of connecting these 3 random variables is to use a conditional Gaussian, whose mean in here is defined by the 2 variables in here. Right? So that's pretty obvious. And in some cases, we may run into hybrid models, meaning that, say, maybe in one case, hybrid model, here you have A being discrete, and B being discrete, and C being continuous. Any idea what should we do? That's to first kind of drag you into the obligation of specifying fancy or reasonable building blocks in graphic model. So these 2 are too obvious. I give you a slightly more challenging one. How to do this? 2 discrete and 1 continuous. What do you do?
You would actually use the values that A and B take on to compute some sort of a Gaussian or parameterize the Gaussian based on the values of A and B.
Okay, that's a nice direction to pursue. Maybe let's be more specific. You can use these 2 values to help parameterizing this as a kind of a conditional Gaussian, right? How are you going to use it? Here are 2 discrete values. Say they can be 0 and 1, 1 and 0, and so on. and how can they be used to reparameterizing or set up a conditional Gaussian here. I heard somebody saying a mixture, right? So that's a very natural thing. Mixture means that you have a number of Gaussian components, and you kind of use these guys as selectors, right, of that. And mathematically, I hope you still remember, we have this trick, P of C given to discrete A and B could be written as, say, a multiplication of multiple, Gaussians. Let's say I and I. That means the i's component. And here I have I over 1 too many. And then I have a delta function, which is an indicator function, say delta A and times delta B. What does that mean? That means, maybe this delta function equals to 1 if the argument equals to 1 and otherwise equal to 0 or something. And then you're going to use this to select one of the components. Right? That's kind of the rough idea. So you need to actually now be familiar with this kind of argument. In fact, this whole table also can be written in this way because you have all these different numbers, right? To select one of these numbers to be the actual probability of a event, you actually are going to use that delta trick to actually generate a selection from multiple outcomes, right? How about the other way around? I have, say A and B both are continuous and C being discrete. What should we do? Any something handy in your collection already?
Use a floor function or something.
What's that?
You can use a floor function.
A floor function, sure. That's very natural, right? You can kind of a step function or something, or just truncate the value to be, say, if these two guys, when them sum together, they are above or below something, you take this to be so on and so forth. That's a nice design. And any other choice which may be a little bit more handy, because maybe you need to, in the future, compute a derivative or maybe a higher order derivative on that. A floor function can be a little bit harder to manipulate. What's that? Logistic. A logistic regression, right? A logistic function. So, basically, it's the output is a binary or even a multi-way discrete function, and the input could be any continuous value or discrete value. Right. So these are basically some of the building blocks that the people already felt very natural about. Now the question is that obviously you can name many other things, and so you actually will be in a big zoo of a variety of options for parameterization. And each of them probably invokes a different learning algorithm. Are there any kind of regulations or their standard or maybe a common practice to make this step easier? Okay, so that's kind of the goal of this lecture. So recall our linear regression, right? So in here, we have a predictive function, which is built on the linear combination of input features. And we can turn this very simple predictive function into a probabilistic model in which we model the noise, epsilon, from this prediction to be a Gaussian noise. Then we can write down a conditional distribution in this form, whose mean is defined by actually the signal, okay, from the input. Okay, and we all know how to actually solve this problem, using a number of methods, including this least mean square algorithm. If you remember, this is about taking the derivative of this square loss function, in fact, which is this term, and then you do a stepwise update. And there are some other means. So this is a form of distribution I think you are already familiar with. I'm going to show you a few more other things. Right. So here there is another function, logistic regression, we just mentioned. Again, the input can be some function of mu, right? Or, I mean, not some function. I mean, the input is x itself. And then we're going to use a logistic function to define the likelihood of the discrete output given the continuous input. And this is the shape of a logistic function. And we're going to skip the discussion on why it's interesting and useful because that's covered in 701. But again, this particular form, once it's defined, allows you to, again, thinking about a proper algorithms to estimate parameters, which is the mu, the theta in here, how to estimate that. And again, we learned a few algorithms. One, of course, is always the so-called the brute force gradient method, just taking derivative over this and try updates. So today, of course, the goal is not to review all these algorithms. We know that already. We're going to actually now examine a few more of common, probabilistic models, and then come to a conclusion or realization that they actually are members of a very big class of distributions known as exponential family functions. Okay, and in fact, what we see here is not only a family of the exponential family function, but also it is a generalized linear model because the way you can see parameters are interacting with the input is through a linear function, even though the entire output has a transformation, a nonlinear one. Okay, and we want to argue that this kind of characteristic is very, very universal to almost all the models that we are going to run into in our machine learning research. And there isn't actually a strong reason to not do that. Some people may argue we don't want to really stay with this model. I rarely see a convincing argument to support that because even if you prefer a nonlinearity, there are also ways to turn them into a linear model. And we are going to see a few examples later on. And again, the motivation for creating this very universal picture is to make the inference algorithm more canonicalized and standard. So again, let me show you a few more examples so that you can appreciate what I just said. So this is a Markov random field. It looks like an odd kind of complex distribution because we talk about potential functions on clicks in the graphs and so on. But now come down to the actual instantiation of a Markov random field on some real graphic model. You'll start to see some actually concrete but very simple examples. For example, here we have the Ising model. And this is built on nodal potentials and the pairwise potentials. The nodal potentials are often just the value of the random variable itself. And the pairwise potential on the edge are often defined as the product of the two variables. Therefore, you can see a weight combination of this and that. Okay? And again, this is exponential family distribution, right? It's actually giving you a exponent and then subject to a partition function. Well, I haven't defined what is exactly exponential family distribution yet, but I'm going to tell you this one is one of the instances. And if you recall, we also studied the RBM. And here, again, we have the nodal potential. We have also the edge potential. And each potential is also weighted by some unknown parameters. And they are to be estimated through some algorithms. So this is, again, another example that reminds you a very familiar form, right? Exponent of some weighted sum of some terms. Okay. And this is yet another example. Remember, we didn't have time to go through this very famous model in our earlier lecture on MRF, but now we can revisit a little bit more. This model is known as the conditional random field, invented here, okay, by our colleague John Lafferty many years ago. And so it is actually also an exponential family distribution in the following form. In this distribution, he proposed to define the conditional probability of the y's, which are the labels, given the observation sequence as an exponentiated sum of weighted potentials. And these weighted potentials are defined, again, on graph cliques. Okay? And in here, the cliques are obviously this guy and that guy, right? So pairwise cliques and also singleton cliques. And again, there is a reason why this model become very popular later on in many places in NLP and in computer vision as a replacement of the hidden Markov model. Okay, there are a lot of reasons for that, but one of the reasons I found to be very, very compelling, actually two of the reasons I found to be very, very compelling are the following. First, it is removing the directionality of influence. Okay, so here you can see all the nodes are undirected. Okay, and in fact, you can make this model more flexible by not only making the indirected, but also make this entirety of X to be influencing every node directly rather than indirectly. In here, every piece of the X is going to influence one of the state, but the rest of the X will be influencing one of the states through an indirect fashion, if you remember. Right? We do full backward algorithm. Once we write down the posterior of P of I given all X, we need to run some procedure, okay, so that all the information gets included. But in here, it is possible to actually write down a potential function of yi or y of yi plus 1 directly as a function of X. What is the benefit of that? Well, sometimes there are properties of the X which is very global, and depending on the configuration, you want the behavior of a single node or a pair of nodes to be in a particular way. For example, after I look at the entire X, entire sequence, I found that it is bold-faced, a very weird feature, right? And if it is bold-faced, I probably can imagine it is an important quote from some person. Therefore, I need to label the terms in the sentences in a certain way. Okay, very reasonable. Or maybe this whole thing is written in a foreign language, even though the whole text is in English. Again, you suddenly need to invoke a different rule of part of speech tagging in every token or every pair of tokens. Right? So that kind of property can be very hard to be included using a hidden Markov model, but in CRF, you can easily design that kind of property. And likewise, you have a similar behavior in image. The whole image may be a natural scene or indoor, so that's not only happening on every pixel, but on the whole thing. Then you can actually define the features conditionally. And the second property is this actually a property of a feature design. So in here, we also have something called a feature design, right? So we have the conditional probability of a yt given yt minus 1 and xt given yt. Pretty much you are restricted by defining a transition probability between two states. And such transition probability probably needs to be defined on all possible state transitions. But in here, you are defining really a potential function, and potential function does not have to obey a probabilistic interpretation. Therefore, they can be a lot more flexible. Right? So here I have a list of guidelines for designing these potential functions. In particular, I made the definition of the potentials, or sometimes called features, to be more explicit. I have the so-called singleton feature, or a singleton feature, which defines on the vertices. And here I have the edge-wise features, which is basically a pairwise potential. And then you can basically define features on every pair of tokens or every singleton tokens. So what does that mean? Maybe it's very hard to imagine, but let me give you one example. Suppose that we are going to use this CRF to parse, to do word recognition or to do speech recognition, and then we have 26 English characters, and therefore for every pair of y, in principle you need to have a table of 26 by 26, which is a lot, right? And so you have to do this. And this is not only rather unnecessary, but also it creates a lot of redundancies. And also, it lacks a insight that certain behaviors are pretty uniform or general for a combination of triplets or doubles. So, for example, suppose we are talking about triplets. Let's talk about even the bigger potential. You probably imagine that the 3-character ing happened a lot in English, right? Maybe likewise, what else? What other ang could be also very often, right? And I don't know, ly may be very often, but you don't actually see ABC together very often, right? So in a sense, you have a way to ignore certain combinations of configuration, but on the other hand, put some particular combinations to bear similar weights. Say they take some substantial weights because they are likely to happen more together, right? And again, because they can be dependent on this x, which is a global feature, maybe the global feature indicates the type of language it is modeling or the context. Then you are going to probably have a more subtle way of biasing these weights for triplets or doubles of characters. So these are what I mean by features or potentials. You basically can build a table telling others how a pair of labels are going to prefer certain configuration over other configurations. And once you have all these together, all you to do is to put a placeholder, lambda and mu, which are the weights or the parameters, and then you have a lot of training sequences. You're going to define the likelihood like this over the training sequences. You're going to estimate the lambda and the mu against that training sequence. Right? So that's kind of the general idea of parameter estimation. But the fact that this model is an example of the exponential family distribution make the procedure rather easy. In fact, the procedure in here is no different from what you do in estimating a logistic regression. Okay? All right. And okay, so here is another example for evasion. Now let's take a look about the common characteristics of all the distribution we see so far. They look all very different, and they were used for different purposes, but they have this fundamental commonality in the way they were put together. They were put together like this. Okay, for a let's first consider just the one collection of random variable x. We don't actually build a complex model like x and y with a prediction from x to y. We are going to touch that later. But suppose we have only a numeric random variable x. The x could be a scalar, it could be a random vector, and exponential family distribution takes the following form. It has the following components. Tx is called a sufficient statistic, which represents either x itself or some transformations of x. Okay, and we can see a few specific transformations later. It's actually likely a vector because you may have different ways of transforming x. So this is a T vector. Let's make it more explicit in here. And then you have another eta vector, which is the weight on each of the sufficient statistic. And then you have this thing called a log normalizer, log partition function, so on and so forth. They are going to be a function of the eta only, not about data. And then you have another h function, which I don't know how it should be called. It's just another kind of auxiliary function to kind of carry any residual effect of the input data. Okay? And this is equivalent to this one once you bring the log normalizer to be a log normalizer itself. Okay, so by definition. It turns out that this form is very general to the point that all these familiar distributions that you ran into before is a special case of this general form. Let's take a few examples. Take a look at a few examples. Say this is a multivariate Gaussian distribution. Okay, and so usually we wrote Gaussian in this way, right? In a linear algebraic form, you have a dot product between the transformed residual on the mean and multiplied by a inverse covariance and then another residual. And these two parameters, sigma and mu, are the usual way we parameterize a Gaussian distribution. They were known as moment parameters. Okay. In the parameterization I talked earlier, I will be with you in a second, we have a slightly different form, which is actually having a very, kind of awkward, but again, unique correspondence to the mean parameters. You just expand all this, okay, into all these base forms, and you just see where your x, showed up, and in what kind of form, and where are the terms does not contain the x. You may realize that these two things actually can be put together, okay, as the first order term and the second order term of the input. And if you concat them into a matrix, into a vector, they become the vector of sufficient statistic. So this guy, you can imagine it could be the x itself, okay, and then here it is the xt. It is a matrix. How do you put a matrix in here? You just take each column and stack on top of them one after another and have a long matrix. So this one is a pretty tall vector. Okay, it has a half of the n squared plus 1, plus n dimensional. And here are the corresponding weights, which actually can be very obvious. It's actually one part is in here, and the other part is in where it's in here, right? So they basically become another actually long vector. And then for whatever other terms that does not include include an x, they become the a components. And then for whatever others that is remaining, it is the hx. In here, it does not contain x. Very, very straightforward brute force mapping between these two. And this one is known as a natural parameter. I understand you may got confused. This is rather unnatural in your looking, but once you see a few more, you will see this is actually more natural than the other one because it is more generic. Question? Mm-hmm.
Why do we need a different T of x and h of x? And what is the significance of sufficiency?
Very good question. The T of x in here, you of course can put this hx exponentiate and put in here and blow up but that's a constant offset which actually does not have to be implemented, have to be estimated. This eta and is the basic the term directly driven by the data point, okay, and the parameters. So there is just a mathematical cleanness in making a exact correspondence between the sufficient statistic and the parameters, the natural parameters. Otherwise, you will redefine the natural parameters to have an offset term, which is a little bit awkward. Okay, yeah.
Why is it then called h of x if it's not really a function of x?
It's not always. It could be sometimes. Yeah. Okay. Basically, it's a placeholder for anything that is not necessarily interacting with the natural parameters. Okay.
But if it is a function of x and you take it into the exponential, then it does become a sufficient statistic, or it doesn't?
Well, sufficient statistic is used to estimate parameters. Okay. If it is interacting with a parameter 1, you don't actually need that. Okay. Yeah. All right. And here I want to just flash at you another example, which is a multinomial distribution. I'm not going to go through that, but you can go home and now establish a mapping that this one, which look seemingly very different from the Gaussian distribution, is yet another example of the exponential family distribution with the following definition of the sufficient statistic and the natural parameters. Okay. And again, there is another reason to define to prefer this, because in a very few slides you will see that there is a very intricate relationship between the natural parameter and other functions in the distribution. For example, you can see that once you take a derivative of a with respect to h, you get some interesting properties. Okay. All right. In fact, it is right here. Now, people ask why we prefer that. Well, because the way we just now used to define a probabilistic distribution makes a few canonical connections rather handy. One is this moment generating property. Okay, many people want to actually estimate the moment of data, right? And why that's interesting? Well, sometimes in fact, very often, moment estimation directly leads to parameter estimation in the model, and this is the reason. For example, suppose we have the partition function, okay, and you take a derivative over the natural parameters. After a few steps, okay, you actually will see that it leads you to an expectation of the sufficient statistic itself. You take a second order derivative, you get the variance of the sufficient statistic. And you can go on and take a third and the fourth, you will get the third order and the fourth order moment of the sufficient statistic. And that's another reason why this X was excluded. Because once it is included, it becomes not so clean, to derive this kind of relationship. Okay. All right. So that basically give us a way of doing the moment estimation. Okay, because you can always actually compute the moment from a sample estimate. You have examples. You basically can get a sample mean or a sample covariance instead of the expectation of the mean and of the variance. Okay, and also that's basically giving you another illustration of the dependencies between these two parameters. You can see that once we establish this, we can define the mean of the sufficient statistic as our mean parameters. Then that basically make explicit a one-to-one correspondence between the mean parameterization or the moment parameterization versus the canonical parameterization. So there is a nice function, okay, mu equals to f of eta somewhere, okay, and that's going to be used later on for you to choose a smarter parameterization, in among many choices. And also, you can for free realize that this log partition function is a convex function because the variance of the sufficient statistic is always a positive semi-definite matrix. Okay. All right. And vice versa, once you have the mean, you can always likewise estimate the natural parameter through an inverse of this function. Okay. Okay. And that basically gives you, again, this very definition of the partition function actually also guarantee you that there is a one-to-one mapping between the eta and that, because you always have it's a convex function, and then you have the mu being the tangent of this particular function. Okay. All right. So now let's see, with all this set up, how can we now estimate the parameters of exponential family distribution? And we learned before that one of the consistent and commonly practiced estimator of parameters in the probabilistic distribution is to use the maximum likelihood procedure. Now let's see how maximum likelihood actually, what kind of result it gives you, under exponential family distribution. It turns out it gives you actually a very nice solution. So we have now the likelihood function defined on data, okay? And that means these x are now instantiated on every data points, and they are multiplied into n copies, okay? And again, taking derivative and doing all that, at the end of the day, your estimate, the MLE estimate of the moment parameter is going to be the sample average of the sufficient statistic, okay? So that's actually a very nice thing, because this form of the sufficient statistic T is very apparent in our definition of the exponential family distribution, right? So if you have a Gaussian distribution or other distribution, what you can do, if you like, is to regroup them into a natural parameterization form, so that the very kind of format of the sufficient statistic is exposed. like what we did in the multinomial and in Bernoulli and other forms. And then you are going to just compute each of these sample mean of the sufficient statistic. Then you get an estimate of all your mean parameters and the second order moment parameters. Okay? And this method is called moment matching. And you can actually also use a transformation, okay, to now retrieve your estimation of the natural parameter, because this transformation is a one-to-one correspondence. Of course, this function itself can be a little bit obscure because it depends on the very specific form of your distribution you use. Okay. I think I have quite a few examples later, but here I want to emphasize a little bit more on the value of resorting to sufficient statistic instead of the real data. So, for especially in the age of large data, say you do in the future, we are going to talk about topic modeling, do many other network inference or something, you are going to be given a lot of data. So there is this fundamental question you will ask. If my goal is to learn the model, say learn a topic model for future use, what should I do with the data? Should I store them? Should I store some kind of higher order or some kind of distillation of the data or something? What can be the guideline? Obviously, storing the entire data can be rather expensive, right? So is there a way to reduce that? Well, the question can be made easy if you are willing to assume that you are going to use certain restricted family of exponential distributions to model your data. That's actually a pretty safe assumption because so far I haven't seen any interesting model not a member of the exponential family distribution. Okay, so here comes a nice insight, which can be found from Mike Jordan's book. There are different ways of illustrating the relationship between the parameter, the data, and the sufficient statistic, but they kind of all give you the same conclusion at the end of the day, which is the following. So from a Bayesian perspective, you basically want to estimate your parameter, and your parameter is going to be driven by the sufficient statistic. You can kind of view the sufficient statistic as defining a prior of the parameters. And then the sufficient statistic is a deterministic function of the data itself. But you can see this guy is sitting between these two, which means what? Which means this one deseparates that from that. So if you are really taking the Bayesian view, you should be assured that you can throw away the real data once you copied all the sufficient statistic. The sufficient statistic is what? Is maybe some the x the value of the x, and that's of course unfortunate because it is the data itself. But sometimes it amounts to the counts on the x, or the counts on a triplet or a product of a pair of x's and stuff like that. So once you see those form of the sufficient statistic, you can actually hopefully get a reduction of your storage. And in here, pretty much you can now have this Bayesian view of dependency between the parameter and the sufficient statistic. The frequentists, of course, don't view the theta as a variable. They shouldn't follow any distribution. They should be an unknown constant underlying, the distribution or indexing the distribution of data now. Okay, not the distribution of parameters. But again, that basically translates to a view like this. You are going to now define the distribution on x, okay, but x can depend on two things. One is the sufficient statistic, and the other is the theta. And once you have the sufficient statistic, you don't need theta anymore. Basically, the sufficient statistic itself purely defines on the x. Okay, this view is a little bit less useful because basically it tells you that storing sufficient statistic is the same as storing the theta, even though what you actually really want to do with the data is probably to get some nice insight which are better reflected in the theta than in the sufficient statistic. Say a regression model, the coefficients give you more information instead of the counts where coefficients are computed from. But anyway, the dependency is pretty clear, that sufficient statistic is sufficient to carry all the informations.
Sorry.
Yeah.
So you are saying the bottom one is less useful than...
Well, I wouldn't say that. I'm just saying it gives you a view which is pragmatically not necessarily practiced by you. Okay, because when you play a Bayesian a frequentist practice, you may still need data, even though you have the sufficient statistic. Okay.
By the frequentist view, does it mean that we can calculate the likelihood of distribution without knowing the parameters?
Yes, in fact that's true. Okay, but the way you do it is to now turn the sufficient statistic into the parameters and compute it.
Right. So
Yeah.
from the data, if we can calculate Tx, then
Yeah.
we need to know the distribution.
Yeah, so the Jordan book talked about sufficiency from a philosophical perspective. I'm talking here in a more pragmatic kind of view, where how you use it. Then I agree that data is still needed in here. Okay. Yeah.
So from frequentist perspective, are you suggesting X is coming from or X is generated from X?
Well, in the frequentist perspective, there is no generative procedure. Okay. Frequentist model is not generative. It's just a distribution indexed by some number. I would say this distribution is indexed by the sufficient statistic.
But we know that X comes first and Tx is kind of the combination.
We don't know. That's what you know. Okay, that's the Bayesian view of drawing a model. The frequentists don't actually produce generative model. There is no Y conditioning on something. Okay, it is a Y in that slash. The thing after the slash is the indexer, not the prior. Okay, that's how frequentists view statistic. Okay. Again, I don't want to really log into this debate. Okay, it is not very meaningful because in modern machine learning, we don't really care whether you call it a frequentist or Bayesian, as long as you write down the equation and know how to do it. So I prefer not to enter that debate. Okay. Any other question in terms of the operation of this principle? All I'm saying that this guy is safe to store, okay, and carries all the information you need for the model. Whether you need to do one more step or not, depending on whether you are frequentist or Bayesian, or whatever Bayesian model or frequentist model you want to use. And maybe Neyman is trying to really reconcile these two. He basically says this only. Okay, so all you need is basically a combination of two factors. One captures the dependencies between these two, okay, and the other is capturing the dependencies between these two. That's the whole thing you need for defining a distribution on the data. And there you actually kind of see the H already. The H is capturing, the part that has nothing to do with the parameter. Okay, it's kind of capturing the dependencies between the X and the sufficient statistic of X, which is a deterministic relationship. Therefore, we can pretty much ignore that in terms of a calculation because it doesn't influence our way of estimating parameters. Okay, the way that influence the estimation of the parameters is in the first term, which is our exponential part of that exponential family distribution. All right. Okay, so that's about a philosophical kind of small discussion on the sufficiency, and the take-home message is that this T indeed satisfies sufficiency, okay, for your model purpose or estimation purpose. And again, here are examples that you can go home and run through to actually get a gut feel about how this generic formalism can be, kind of realized on different instantiations. All right. So I want to say another few words about Bayesian statistics in the context of the exponential family distribution. In particular, many people talk about conjugate priors or choice of a proper Bayesian priors. And we actually, I think in our machinery class, we talked about what is a conjugate prior, right? Which basically says posterior under such prior should take the same form of the conditional and so on and so forth. Here I offer you a slightly different way of saying the same thing using the exponential family distribution language. So suppose we have X, right? And we assume that X follow a exponential family distribution. let's forget about h and put it like this eta vector and the t of x and minus a of eta, right? So that's a pretty nice thing. And what does Bayesian bring us to? Well, if you are a Bayesian, you cannot believe that this eta should follow a prior distribution because eta is the parameters. And well, we can assume it is now following another exponential family distribution, okay? And maybe we should call it Kasai, for example. And now we have a sufficient statistic defined on eta, right? And then that gives us a function of, no, I think Kasai, right? Okay, so now let's take a look of the posterior. So what Bayesian enables you to do after you have the prior and the likelihood? What you want is a posterior, right? Which is basically a p of eta given the x and given the Kasai, which is the hyperparameter, right? So how does that look like? Well, if you put things together, you will see some interesting insight. You have the first term, which is eta times xt. And then you have the second term, which is the Kasai times a t of eta. Okay? And plus something, some a's. Okay? All right. So this is basically a distribution which you are supposed to deal with. Now, if I make a interesting assumption, which I assume that, what about, say, making eta in here equal to the sufficient statistic of eta? What if this happens? Then we actually can derive that exp of what? Right? Something like that. Right? Okay. So that's pretty much what explains a conjugate prior. If you compare the posterior and the prior, okay, you actually now realize that they actually took exactly the same form, except that in here, the sufficient statistic of the posterior has the data term in addition to the prior term, okay, in here. Okay? See that? So that's basically another way of understanding the conjugate prior. If the natural parameter in here has the same form in its sufficient statistic in its prior, then we call it a conjugate prior, and that produces a posterior distribution which looks the same as the prior distribution. Okay. Again, so it's basically that gives you the guideline of choosing the conjugate for all the exponential family distributions now. Okay, you don't have to guess in whatever way, how to make sure the posterior is equal to the prior. Okay, so for Gaussian, for multinomial, for many other things, they all follow the same rule in here. That's kind of a handy realization. Okay, so now any question before I move on to some slightly more challenging material here? Because what we talked earlier is about p of x. Okay, now let's study how to use this technique to parameterize a conditional distribution. Because in graphic model, what we need, this one is only useful for defining the marginal on the node, on the root of the graphical model, right? But if you want to define, a conditional distribution, inside the graphic model, you need to at least know how to do this, and how can we build a exponential family for these kind of models. That's the question. So we talk about, we start by a very simple case because that's, once we know how to do that, we pretty much can extrapolate to other forms. And this is let's assume it is a linear regression, for example. And we actually want to observe a common property we want to use, which is we want to use some kind of linear transformation of the input to define the mean of the observation. Okay, so that's kind of a common property we want to actually use. And then the question we are left to answer is this expectation is defined on what function, what distribution. That basically defines you kind of the noise distribution over the signal. And the other is what this transformation function should be defined. Okay, and you can now go home, or maybe not go home, just sitting here and play a little movie of what you learned before. You probably can now establish correspondence of this definition to many of the stuff you learned before, right? For example, what is logistic regression correspond to? Right? That's roughly, this one corresponds to a linear function, that one corresponds to a sigmoid function, right? A linear regression, probably this one corresponds to a Gaussian distribution, this one corresponds to an identity function. So somehow you can build these connections now already. And this if we go general, making this not just an identity or a sigmoid transformation, you actually now come to a very big family of distributions known as the generalized linear model. Okay, it contains the following components. First, the observation, the input, okay, is assumed to enter the model through a linear combination of its element. So we need to produce psi through a weighted combination of all the x components. That's the first step. And then the conditional mean of the output is represented by, a transformation, okay, which is known as the response function. And you are offered, all the flexibility of defining them in different way. But there are certain better definitions, as we will see later. And then the observation, y, is going to be characterized by this mean distribution through an exponential family distribution. Right? Remember that in our exponential family distribution, we need to have, so here is the confusing part I want you to pay attention to. Here we have the natural parameter and the t of x, which is the sufficient statistic of the data, right? So this is used to define distribution over x. Now here we want to define a distribution over the y, okay? Therefore, we actually need some t of y here. And the only way that x can enter this distribution is to influence the way eta is defined. Okay, so we basically have eta here, and the eta come from a f of, basically come from mu, for example. Remember, mu and eta had this one-to-one correspondence. The mean parameter and the natural parameter has this one-to-one correspondence. And then mu is actually coming from f of theta x. That's kind of the rationale behind this design. Okay, it's a generalized linear model because now your eta, which was originally a unknown constant, is now becoming data dependent. Okay, it depends on a part of the data. Just to repeat, this is the whole picture. I'm going to reiterate a few points. You can find the same graph on Mike's book, right? A part of the data enter from here, and then they generate a response. Okay, the response is transformed into the mean parameter through a response function. Okay, and the mean parameter is corresponding to a natural parameter through this mapping function, and the natural parameter is used to define an exponential family distribution of the other part of the observation, which is the response, the output. Okay, and this is made clear in this whole equation. Any questions? Okay, let me maybe have a few, yeah. The other way to understand it is that you start with this, you really, get a way to influence the eta, and the eta will now be combined with the output, and then you are going to define the conditional probability of the output given the input. Okay, so that's basically the story, how the story goes. Okay, so the exponential family, of course, this one, the choice of distribution is solely now defined by the nature of x, whether it is discrete, it is continuous, it is multivariate. What that defines how you are going to choose the eta. But the x is now swept under the rug because they only are going to be used to define the main parameters. Okay, and then there is this very interesting part of defining, choosing the response function. Okay, and here there are something that you can take advantage of the fact that the whole design is a generalized linear model. Because in the natural parameterization, what we actually want to use is the eta, which actually requires a mapping from the mean parameter. So there is this mapping function, psi. Okay, and then here is another response function to do this to map this into mu. So what if I make this one an inverse of that, like what I said here? Any insight? Once I did this one become inverse of that, how the eta would look like? The eta now becomes this. Okay? That, again, is another important trick people want to use to reduce the complexity. Yeah, you lose some flexibility because now you fail to have a nonlinear response, okay, from the input. But you are actually now in the much easier paradigm of parameter estimation where estimating the eta is equivalent to estimating the theta, which were originally used to weight the input features. Okay? And if you really, really want a nonlinear function from input to output, there are two places for you to play. Somebody can suggest? What if I want nonlinear? Two places to still kind of enable nonlinearity. You don't have f anymore because f and the psi become cancelled. Apply a function to, okay, so you are saying that this choice of the exponential can be made fancy, right? Well, yeah, that's partially true if you want to stay beyond the exponential family distribution, because in exponential family distribution, the eta is a linear function, right? In fact, there is only, if I stick to that, I have only one choice left to make them nonlinear. I just want you to remember, which is the very feature itself. You can basically create higher order features by making x squared, polynomial of x, everything, kernel of x, into the feature itself. Okay, and then they become a richer input data set. So this one can actually become a vector of f, x, something like that. Okay, just to turn them nonlinear. But again, these are just additional random messages, which is not essential for this lecture. And here, I want you to at least stare at some of these forms to realize a few instances of this so-called canonical response functions, okay, which actually made a truly linear relationship between the input and output. All right, so once we have that, everything is made easy now. Okay, we do actually came to a canonical formula for parameter estimation. So you have the likelihood function, you make the derivative, and I hope everybody know how to do that already, right? So this derivative gives you the mean, and this one gives you what? the eta and the theta, or they give you 1 because they are equivalent if they are natural response. Therefore, you have this, and at the end of the day, you compute the derivative like that. So this is now what? A fixed point iteration, basically, right? In fact, I had some little mistake in here. I should have written mu here, because here the theta is actually mu. There is no theta. Is there? Oh, no, there is theta. Yeah, sorry. And then, we'll have a fixed point equation, because this mu is actually a function of theta, right? And then, what you do is to iteratively, update the theta until you converge. And here is the learning step. And this is all very familiar, least mean square, okay, for, a simple expanded family distribution. But in here, I assumed some very easy form in here, so that this derivative is actually unity. So some people dislike this approach for many reasons, and one of the reasons is that this row step size can be a little bit tricky to tune. And if you remember our earlier lectures on second-order methods for gradient, you probably also remember this, right? There is a Newton method where we can avoid computing the step size by using a Hessian to recalibrate the gradient, right? And the computing Hessian, of course, is not an easy step, but it gives you the right step size. And here there are some algebra, which is kind of fun to read, but I'm not going to go through there. You actually can compute the Hessian function, okay, in a closed form. Here, you actually need to compute this very interesting W matrix, which is a diagonal matrix of the gradient of the mean parameter versus the natural parameter. Remember, there is this mapping function from the mean to the natural parameter. You need to take derivative of that. Okay. And this is, again, a very generic update function to any expanded family distributions and generalized linear models. And with that, you actually get a canonical learning step, which I'm going to actually show you after I actually remind you about this equation. So remember about this one. This is our very familiar linear regression, and by minimizing, the squared residual, we know that we can solve this problem through something called a normal equation. You remember that, right? So normal equation is a single-step solution where you compute the pseudo inverse times, the design and times the response, single step. We can argue, of course, whether it is a good thing to do, but suppose you can do it. This is a very clean equation. Now, suppose now our estimator is no longer a linear regression, but a more fancy one, and we want to use a Newton-Raphson method like we did before, then this is the updated equation, right? And we knew that h and the gradient can be all computed in closed form. Therefore, you actually have this update to take the following form, which a little bit weird, but I'm sure you can work it out just by adapting equations and introduce this definition. But here, I want you to pay attention to the symbolic similarity of this one to that one. Okay, that's actually the insight I want to deliver. So this thing is sometimes known as a iterative reweighted least square estimation for the following reason. So Z is now by definition, a shifted and the reweighted version of the true response Y. Okay, originally you have this real response Y, which you observed, and built on that, and using your current estimation of the theta and some other thing, you get a Z, which is known as the reweighted response. Okay, and then now if you compare this guy and that guy, you actually will see they are symbolically very similar. Okay, Y here, the true response, is now replaced by the reweighted response. The original design X is now replaced by the weighted response. Okay, so in a sense, you can now view this solution as solving the so-called reweighted least square problem, from which we actually solve the normal equation. In here, you have the reweighted normal equation. You actually get this thing. Okay, and that's historical how people explain this solution, and in their connection to the original normal equation. But there is a key difference in here, which is here your normal equation is a one-step solution. Okay, you have the x, you have the y, you put them together, you compute theta in one single shot. In here, what's going wrong? Can you do it in a single shot? Why cannot? Because this z actually has a theta there, which makes them a fixed point equation. Therefore, you can only do it iteratively by starting from some random theta and then iteratively use this update, and at the end of the day, converge to some point. Okay. But the nice thing about that is that this particular update is generic for any exponential family distribution. Okay. The only difference is how this W is computed. So in the case of a logistic regression, your W is computed in this way, and then you can use that to solve the theta estimator. And in I think some other linear regression, you also have a W which is now become very simple identity. Then you get another solution. Okay, so that's basically what I want you to take home. A generic maximum likelihood estimator of the exponential family distribution or the generalized linear model. Okay, using a Newton-Raphson method. There is this first-order gradient and the second-order hashing function. Of course, if you don't like Newton-Raphson, you want to use other methods, then this piece of information is a little bit less useful. But at least, if you don't want to do any derivation, this one gives you a guaranteed convergent algorithm for learning the generalized linear model. Okay, I think I'm roughly done with the bulk of the lecture. There are a few slices I left over, which actually is a good material for you to go home and read. Basically, it tries to tell you that once we know how to define a conditional distribution of a pair of nodes using a Glean model, we can now define any graphic model in the same way, right? For example, here I told you before this graph of graphical models. Smaller graphic model is a building block of the larger graphic model. Therefore, all you do is to multiply multiple Glean models together to build a larger one. Therefore, we actually now have the generic building blocks for probabilistic graphic models using the Glean and the generalized linear model. I think I want to conclude here. I'm going to spend some time in next lecture to talk about how to define proper priors on complicated multivariate graphic models, using the same principle, but I'm going to present that in the context of a specific maximum likelihood estimation context. So let's stay tuned for a next lecture. We have a question over there? Yeah.